Alright, in this video we'll be going through the 2023 Waves exam. The way I recommend you watch this video is to pause the video before every question, try the question yourself. Once you've completed the question or get stuck, unpause the video to see how I go about getting the answer. A violin is a stringed instrument onto which the strings are fixed at both ends. The fixed points are 0.331 meters apart. Sam plays the violin by making the strings vibrate by pulling and pushing a bow across the strings. One string, called G, is arranged to play the fundamental frequency 196 Hz. Calculate the speed of the wave that travels along the string. Alright, so this is a simple question. We know that the velocity of the wave is equal to our frequency times our wavelength. We are given the frequency right here, and we know that our length is directly proportional to our wavelength. In this case, we have a situation where our boundary conditions are fixed at both ends, meaning we can draw out the string like so, and we are playing the fundamental frequency, so we have nodes on both ends, and this is an antinode, okay? And from here we can see that our length is equal to 1/2 of a wavelength, and so therefore 2 times our length is equal to 1 wavelength, and our length is given right here as 0.331, and so 2 times 0.331 is equal to our wavelength. And so now we can simply plug this in to here and plug our frequency into here, and we get the velocity of the wave is equal to our frequency, which is 196, times our wavelength, which is 2 times 0.331, and this gives a velocity of 129.752 meters per second, which we can round to 130 meters per second. There we go. Analysis of the sound produced by the vibrating string shows that it also vibrates at 392 Hz and 588 Hz. State the harmonic that causes the 588 Hz vibration. In your answer, you should include the sketch that shows the location of nodes and antinodes. So in order to find which harmonic causes the 588 Hz vibration, we can use our equation where our Fn, okay, is equal to NF1. And so where this comes from, if you remember, if we have our fundamental frequency, which we can call F1, and we want to calculate our second harmonic, we can go 2 times F1. And for our third harmonic, we can go 3 times F1. And so if we want to calculate our nth harmonic, which we don't know what that is yet, we can just simply take n times our first harmonic. And so therefore, to find our n, which is the harmonic that is being produced, we can take our Fn all over our F1 and we get our n. And so in this case, our Fn is 588. So 588 all over our F1, which we know is our fundamental frequency. And so that's 196. And this gives a value of n as 3. And therefore, this is the third harmonic. Alright, now drawing out the third harmonic where we have the boundary conditions where the string is fixed at both ends, okay? And so therefore our third harmonic is going to look like so, roughly like that. There we go. Sam plays her violin with a fundamental frequency of 196 Hz. As she sits on a moving trailer, the trailer is moving at 5.3 meters per second directly towards microphone A. Calculate the frequency recorded by microphone A. Alright, so we have our Doppler equation where we have our perceived frequency is equal to the source frequency times the velocity of the wave all over the velocity of the wave minus the velocity of the source, using minus in this case because we are approaching microphone A. Okay? Again, if you don't know where this equation comes from, I go through it in my Doppler videos on my Waves playlist, so you can go check that out. But we know the source frequency as that's 196 Hz. We know the velocity of the source because it's traveling at 5.3 meters per second, and we know the velocity of the wave as it's given up here as 342 meters per second. And so now we can just simply plug in our numbers. We have our perceived frequency is equal to the source frequency, which is 196 Hz, times 342 meters per second, all over 342 minus 5.3 meters per second. And this gives a perceived frequency of 199.1 Hz. There we go. Microphone B is directly behind the moving trailer, whereas microphone A is directly in front of the moving trailer. Explain how the motion of the trailer with Sam sitting on it playing the violin affects the frequency of the string, the speed of sound in the air, and the wavelength of the sound in the air in front and behind the violin, and the frequencies detected by A and B. The frequency on the string moving does not change the frequency on the string, and therefore it does not change the source frequency, so you can just write that in. The speed of sound in air, same thing, there's going to be no change in the speed of sound in air because moving with the violin does not affect that at all, so you can again write that in. However, the last two is really where the question starts. If we were to simplify this diagram and draw the trailer as a dot, okay, and we are looking from the top point of view now, okay, from a bird's eye view. As this trailer moves to the right and it produces wavefronts, it's going to catch up to previously emitted wavefronts, like so. And because it's catching up to previously emitted wavefronts, the wavefronts on the front are going to be bunched up, whereas the wavefronts at the back are going to be spread out. And so if we have microphone A here, and then microphone B over here, if we imagine what these two microphones are going to perceive, microphone A is going to perceive shorter wavelengths, okay? And therefore, as V is equal to F lambda and F is equal to V all over lambda, as the velocity of sound does not change in air, because we just established that in our second point, okay? And therefore, if microphone A perceives shorter wavelengths, it's going to perceive a higher frequency compared to the source. On the other hand, B is going to perceive longer wavelengths, and therefore, again, as V is equal to F lambda and F is equal to V all over lambda, if B perceives longer wavelengths, it's going to perceive a lower frequency, again, compared to the source. And you can write that in. On a hot day, the violin easily goes out of tune. Sam has to adjust the tension in the string to keep the G string so it will still vibrate at 196 Hz. Describe what happens to the fundamental frequency of the string when the string gets longer, and nothing else changes. So because we know our length is directly proportional to our wavelength, if our length increases, this means our wavelength will also increase, and therefore, as we know, V is equal to F lambda, because nothing else changes and therefore the velocity of our wave does not change. If our lambda is going to increase, this means our frequency must decrease. Sam uses a tuning fork that will vibrate at 196 Hz. She plays the string while sounding the tuning fork and hears beats. Describe what is meant by a beat and explain why beats are heard. So beats are when you have two waves that are very, very close in frequency, and so therefore if you observe those two waves at a fixed point, due to the slight differences in phase between the two waves, they will continuously come in and out of phase. And so when the two waves are in phase, they will constructively interfere and then produce a loud sound. However, when they are out of phase, they will destructively interfere and produce a quiet sound. And so because they are repeatedly coming in and out of phase, you hear a loud, quiet, loud, quiet, loud, quiet, loud, quiet sound. And it results in sort of a beating sensation. And so you can write that in. Sam hears a beat of 2.1 Hz. Determine the possible frequencies at which the string is vibrating. Okay, so we know the equation for our beat frequency is F beat is equal to the absolute value of F1 minus F2, okay? And so obviously we know that FB is equal to 2.1 Hertz, okay? There are two situations that we need to consider. The first situation is when F1 is equal to 196 Hertz, which again we know is the fundamental frequency. And the second scenario that we need to take into consideration is when F2 is equal to 196 Hertz, which again is the fundamental frequency. And so we can do those two scenarios right here. 2.1 is equal to the absolute value of 196 minus F2, and therefore F2 is equal to 196 minus 2.1, and we get F2 is equal to 193.9 Hertz. All right, and now for this scenario, we get 2.1 is equal to F1 minus 196 Hertz, and we get 2.1 plus 196 is equal to F1, and therefore F1 is equal to 198.1 Hertz. Okay, and so these are the two possible frequencies that the string is vibrating at. All right. She increases the speed of the wave along the string by increasing the tension in the string, and the break frequency increases. Use this information to determine the frequency at which the string was vibrating before the adjustment. So because the length of the string has not changed, therefore our wavelength also does not change, okay? And so therefore, due to V is equal to F lambda, if our lambda does not change, however our velocity has increased, therefore our frequency must increase. And so if we look over here, we can see that our beat frequency is equal to 196 plus or minus 2.1 Hertz, okay? And so now if the beat frequency increases to, let's say, 196 plus or minus 2.5, let's say, okay, this arbitrary numbers. If the beat frequency increases, that means it's becoming more regular, like the beating sound is becoming more regular. So it's went from boop, 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 boop to boop, 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 all right? So it's becoming more and more regular. So that means the frequency has to increase, okay? If we take the case where it's a minus, okay, in this case, let's say we're taking the case where it's a minus 2.1, and that would equal to 193.9, okay? And let's say this beat frequency increases to 2.5, okay? And therefore, this will change to 193.5 Hertz. And as you can see, the beat frequency has decreased in this case. And so therefore, we must take the case where it was originally a plus, and so that was 198.1 hertz, and therefore, let's say it increases again to 2.5. Remember, this 2.5 is an arbitrary value. I'm just showing it for demonstration purposes, okay? So now it increases to 2.5, and our beat frequency is 198.5 hertz, and as you can see, our beat frequency has increased. And therefore, our beat frequency FB must have been equal to 198.1 hertz. Alright, explain what Sam must do to get the string to vibrate at 196 hertz. So we discussed in before, when she increased the tension in the string, that caused the beat frequency to increase. So if we want the beat frequency to decrease instead, we can just reduce the tension in the string. And so what this will result in is a decrease in the wave's velocity, and therefore as v is equal to f lambda, as our lambda is going to remain constant because the length of our string does not change. Therefore, if our velocity in the wave is going to decrease, our frequency is going to decrease, and hopefully it decreases to our first harmonic, which is 196 hertz, okay? State how she will know when the string is vibrating at 196 hertz. If the string and her tuning fork are both vibrating at 196 hertz, there is going to be no difference in frequency between the tuning fork and the string, obviously because they are resonating at the same frequency. And so therefore, by definition, beats only occur when there is a difference between the two frequencies. And so if there is no difference between the two frequencies, that means no beats will be heard. And so therefore she would hear a steady 196 hertz tone. And you can write that in. When Sam plays the frequency 564 hertz near a wine glass, the wine glass rattles on the shelf. Give an in-depth explanation of this phenomenon by describing the phenomenon and explaining how she might stop the wine glass from vibrating when she plays the violin. So this phenomenon is called resonance. The wine glass is being shaken at its natural frequency, and this results in energy being added into the system, so the oscillations build up and up and up. And this causes a maximum in amplitude, and therefore the wine glass is going to rattle on the shelf. And so that is our first point. Our second point is we need to change the natural frequency of the wine glass, okay? As I stated in point 1, the reason why resonance occurs is because energy is being added at the natural frequency of the wine glass. And so if we change the natural frequency of the wine glass, energy will no longer be added at the natural frequency because the violin can't play that natural frequency, okay? And so we can change the natural frequency of the wine glass by adding, let's say, water in, okay? Water would work. If you add water, the natural frequency of the wine glass will change, so you can write that in. At a fair, children are buying rainbow glasses made of diffraction gratings in a cardboard frame. Steve shines a laser pointer through one of the diffraction gratings onto a wall. The laser pointer produces a light with a wavelength of 643 nanometers. The light makes a pattern on the wall with bright red spots at the center and with slightly dimmer red bright spots on either side. The wall is 1.3 meters from the diffraction grating. The distance from the central bright spot to the second slightly dimmer bright spot is 1.75 meters. Describe diffraction. So diffraction is when waves spread out when they are met with a gap or an obstacle in their path. Okay, so if we have waves right here and we have an obstacle like so, as the waves go through this obstacle, they're going to spread out like so. Give an in-depth explanation why this pattern is observed by explaining how diffraction and interference causes bright spots and explaining why there are large sections where there are no light in between the bright spots. So as the wave goes through the diffraction grating, it's going to spread out. Each slit in the diffraction grating is going to act like a source. And so as each wave propagates from those slits, they are going to interfere with each other and overlap. When the waves arrive in phase and therefore their path difference is a whole number of wavelengths, they're going to constructively interfere and therefore produce a bright spot. Okay? When the waves meet out of phase and their path difference is a non-whole number of wavelengths, then they are going to destructively interfere and therefore produce a dark spot. Okay? And because we are going through a diffraction grating, there are many slits and therefore many makeshift sources. Because remember, each slit kind of acts like a light source. And so because of this, the waves are more likely to arrive out of phase than they are to arrive perfectly in phase, okay? Because even if the waves are slightly out of phase, that's going to cause some minor destructive interference. Not total destructive interference, minor. They only constructively interfere when they are perfectly aligned. However, if the waves are even just slightly out of phase, they're going to slightly destructively interfere. So it's more likely that the waves arrive out of phase than they arrive perfectly in phase. And so if we have many sources, this causes large regions of dark spots compared to bright spots. And what that causes is we would have our distinct bright spots with major dark regions in between our bright spots. Okay, so these are our dark regions and dark regions. And obviously, the same thing will happen on the other side, okay, like so. And you can see that in this diagram right here. Here we go. Calculate the slit separation in the grading. Okay, so remember our slit separation is our d value, and we know n lambda is equal to d sine theta. Okay, now we are given our wavelength of light that is given up here. Okay, and our n and our theta are linked together. I'll show you what I mean by that. If we have our diffraction grading right here, okay, and then we have our central maxima, our first order maxima, and our second order maxima, and we would obviously have the same thing on the other side, okay? And again, we have our light waves coming through here, okay? We're going to have our first order maxima, and we are going to have a second order maxima here, and this angle we can call theta. We are given the distance between our central maxima and our second order maxima, so that is equal to 1.75 meters, okay? And the distance between the diffraction grading and the wall is also given right here as 1.43 meters. So this distance right here is 1.43 meters, okay? And as you can see, we have a right angle triangle here, and we have the opposite side and the adjacent, and so we can say that theta is equal to the inverse tan of 1.75 all over 1.43, and this gives us an angle of 50.746 degrees, okay? And so now that we found our angle, we know our n value is going to be equal to 2. The reason for that is because the angle that we calculated is between n is equal to 0 and n is equal to 2. And so if we plug in this angle into here, this equation will only be valid if we respect the fact that this angle is between n is equal to 0 and n is equal to 2. Okay, and so now rearranging for d, we get n lambda all over sine theta is equal to d. And so now plugging in our numbers, we get 2 times our wavelength, which is given up here as 6.43 times 10 to the negative 7, all over sine 50.746. And this gives a d value of 1.66 times 10 to the negative 6 meters. There we go. When the children look at a spot of white light through the glasses, they see a white spot with spectra on either side, which they describe as rainbows. Give an in-depth explanation of this phenomenon by describing where the spectra will occur, explaining the position of the colors in the spectra, and explaining why they are at these locations. So this is our classic question that is in basically every single exam. We know that our central n is equal to 0 maxima, which is going to be in the middle, obviously, because that's the n is equal to 0 maxima, is where all light converges. Okay, so all the waves converge at that point. And so if we shine white light through our diffraction grading, right? We're shining white light through our diffraction grading. Our n is equal to 0 maxima is also going to be our white bright spot. Okay, so this is going to be white. However, what we also should know is that white light contains all wavelengths of the visible spectrum. And what we also should know is that every wavelength in the visible spectrum has different wavelengths, obviously. And so therefore, we should know that red has the highest wavelength, and violet has the shortest wavelength, okay? And so therefore, as n lambda is equal to d sine theta, okay, because d remains the same because we're shining the light through the exact same diffraction grading, and our n we don't really need to consider in this case because we can just set n is equal to 1 for our analysis. If we consider red light, we would have a greater wavelength, and therefore our theta value must increase. And so if we have our spectrum on either side, like so, our red value is going to diffract more, and so our red is going to be over here. And so we can call this theta r for our red value. And the same thing on the opposite direction will be over here. So this will also be red. This is again theta r. On the other hand, our violet is going to have a shorter wavelength, and therefore the theta value is going to be less. And so it's going to diffract less. And so we can call this theta v. The same thing again in reverse will happen over here, where this is our violet, and this is again theta v. And then every other color in the spectrum is going to be in between these, okay? And so what this results in is a white central maxima, and then what the kids would call rainbows on either side. Again, if you want more on this, I go through this in part 2 of my interference video on my Waves playlist, so you can go check that out. And so if we were to draw this over here, we would have our white central maxima, which we can label W, and then we would have our spectra on either side, and we would have red over here, which we can label R, and then violet over here, which we can label V, and then we would have everything else in between. And with that, we're done. See you.